I'm going to be looking at step 3, question 4 from the year 2017. For any function f satisfying f of x is greater than 0, we define the geometric mean f by this. The function f satisfies this condition, so it's always greater than 0. A is a positive number. Prove that this is the case. Okay, so what it looks like, well, before I even jump into a step question, I think it's important just to anticipate what your next few moves are going to be. So what we've got at the moment is we've got obviously something which is E, which then becomes A. And we've also got ln, which we should know is log base E, which then becomes something which is log base A. So what I'm thinking of is a change of base. See if we can change this ln to a log base A. Right, so here we go. So I don't actually know it off the top of my head, but we can have a go at proving it. So let's imagine that log base A of B equals C. Raising all of this to A, we get, raising this all by as a power of A, we have B equals A to the power of C. And then we can log both sides to some other constant, call it K. Use the power, bring the power down, because when we log, obviously we can bring the power down. C is log base A of B. So by dividing by log base K of A, we get our identity here, log base K of B divided by log base K of A equals C, which is log base A of B. Okay, so knowing that, I'm gonna rewrite this. So ln of f of x, or log base E of f of x. Okay, well that can be written as, well in this case A would be E and B would be f of x, so it would be log base A of f of x divided by log base A of E. Okay, so applying this to this, what we have at the moment is that this f of y, the geometric mean, is e to the power of 1 over y times the integral between 0 and y of what we've got here. Okay, so just write that in. Okay, now log base A of E is just going to be some constant. So I can actually factor this out. Okay, I can factor out this log base A of E. Okay, so this will actually end up going outside of the integral. So what I'd have is, I'd have e to the power of 1 over y log base A of E. Now, what might be a good idea is, well, it's going to be e to the power of this, isn't it? Okay, and then obviously we've got the integral here, which is got log base A of f of x. So it'd be good if we could do something on this log base A of E. And I think we can actually. So let's just say that if we could write it as ln, so sort of like put it back as a natural logarithm, we might actually be able to do something about this. Okay, so let's say that log base A of E equals some number, equals something, k. So that means that e equals a to the k. If I ln both sides, I get 1 equals k ln of a. So k, which is what we've got here, log base a of e, k is 1 over ln of a. And k is log base a of e. So actually what this ends up being is e to 1 over y, and then 1 over, well, log base a of e is 1 over ln of a, so it's going to be ln of a times by this integral that we've got here. Okay. Now what we should see is that this is a product. This is 1 over y times ln of a times this integral. And, well, what we can say is, if I just carry this on down here, is, well, e to the ln of a all to the power of 1 over y integral what we've got here, 0 to y. I'm not writing it out all the time because this software's a little bit annoying, but this, remember, a power to a power, it multiplies, and this is just going to simplify down to a. So what we end up with is a 1 over y, the integral between 0 to y, log base a of f of x dx. Okay, so that's the first part done. Okay, next part of the question. Just scroll up. Okay, the functions f and g satisfy the condition that the question has told us from the beginning. Their geometric means are this and this. Show that h of y equals, okay. So this is what we've got at the moment. So we've done this, but I can't see any immediate reason why using this one is going to make any grand difference to using this one. I'm just going to use this top one here. So h of y, that's going to equal e to the power of 1 over y times by the integral between 0 and y of ln of h of x. Well, h of x is f of x, g of x. Okay, I can already see, and maybe you can already see how this part's going to fall out. Okay. Well, we should know that ln of a times b, which is what this is, can be written as ln of a plus ln of b. So this is going to be able to be split up. So if I just, instead of rewriting it, if I just rub that bit out, what we'll end up with is, let's put another bracket around this, ln of g of x. And once again, as this is, say it's all multiplying together, we should know that as well e to the power of, well, I mean, I didn't have to pick e, but e to the power of, say, x times e to the power of y gives you that e to the power of x plus y. So this is going to be a product of two geometric means, which I think is what they're called there. Okay, so h of y is going to equal e to the 1 over y times the integral of 0 to y of this, so ln of f of x, and multiplied by e to the 1 over y, the integral between 0 and y of ln of g of x. Okay. I should probably write the dx's here as well. You know what? Just pretend they're there for now. Okay. So, well, what is this? Well, this is h of y equals, well, this is the geometric mean of f, and this is the geometric mean of g. So it will be f of y, g of y, which I think is what I wanted. Yep. Okay. It's not too bad. Next part. Prove that for any positive number b, the geometric mean of b of x is b of b to the power of y. Okay. Now, as our function f of x is going to be b to the x, I've got a funny feeling that I actually want to use this version of the geometric mean, not this version, because I can choose a to be whatever I want. Okay, so I could say when a is b. Okay, so the geometric mean is going to be, so if I call f of x this b of x, well then my geometric mean is going to be e, actually no, I'm not going to be using e, I said I'd use b to the power of 1 over y of the integral between 0 and y of log base b of b to the power of x dx. Now hopefully we can see why that was a good choice using this one. Okay, as this is just going to, well, the power is just going to come down, it's just going to become x, so let's just get rid of all this, and we get x dx. Okay, so integrating this part, this is going to be b to the power of 1 over y, and then we've got x squared over 2 when we integrate it, y and 0. Well, that's going to be b to the power of 1 over y times y squared over 2, y squared over 2, which is b to the power of y over 2, which is b to the power of y all to the power of a half, which, as we can see, will give us the result. So root by. Okay, so nothing too bad so far. So well, up to this final part of the question. Prove that if f of x is greater than 0 and the geometric mean is root f of y, then f of x has to equal some constant to the power of x. No, yeah, okay. Alright, so sort of this one we're going to work backwards. We know what this is, okay? So we know that our answer has got to be f of y, or the square root, sorry, of f of y. And that's going to equal some number to the power of 1 over y times the integral between 0 and y of log base a. Actually, why are we using, well, let's say we. Why am I using base A? I just think everything looks a little bit nicer when you use ln. So e ln f of x dx. Okay. Now, what I'd be tempted to do here is natural log both sides, so I'll end up with half ln of f of y equals, if I natural log this, I'm going to end up with 1 over y times the integral of ln of f of x. Okay. Multiply both sides by y, so y over 2 ln of f of y equals this integral. Okay, so at this moment you should really be thinking that we're going to end up with some kind of differential equation, or at least that's what I'm thinking. Okay. Now, this, the integral of this is, well, let's say, I shouldn't really use a capital F because that's been defined differently here, but let's say the integral of this is some function g. Okay, well, what we're going to end up with is g of y minus g of 0. That's just a fundamental theorem of calculus, so this is what this is going to integrate to. So if we differentiate it, what we're going to be left with, well, the derivative of this is a constant, so that's just going to go. G is the integral of this, so the derivative would just be this. So when we differentiate this, we're just going to be left with ln of f of y. Okay, when we differentiate this side. Okay, so differentiating the right-hand side is actually a heck of a lot nicer than what we're about to do. Which is differentiate the left-hand side. So it's two functions multiplied by each other, so using our product rule, this would be 1/2 ln of f of y. So I've done the easy one first, and then plus well, y over 2 is going to stay, but differentiate ln of f of y, it's just going to be f of y on the bottom, and then f dash of y on the numerator. Okay, so you should really be getting the idea that this is going to end up being a differential equation at this point. Let's multiply everything by 2, might be a good idea. So we'd end up with ln of f of y. You know what, I'll try and be smart and just get rid of that 2, get rid of that 2, and just stick a 2 here. Well, actually I'm going to put it up there. Okay, because then what I can do is bring this over, so ln of f of y minus ln of f of y squared, f of y minus ln of f of y squared plus y of f dash of y, all divided by f of y, is going to equal 0. Now, this log of a minus log of b is log of a divided by b. So this is going to be ln of 1 over f of y. Well, that's ln of f of y to the power of negative 1. Ln of f of y to the power of negative 1 is minus or negative ln of f of y. So this will just simplify to negative ln of f of y. Now, if you're not too sure where that's come from, just write it out. Literally do ln of a divided by b, and you'll see that you'll end up with something like this. Okay, so plus y f dash of y over f of y equals 0. Okay, so we can actually just bring this over to the other side and it would be positive. So if I just get rid of that, oops, change that to an equal sign, might be a good idea. So that would be positive, so there we go. Right. Alright, so where are we going to go from here? Well, I'll get everything that's to do with f of y on one side and everything that's just y on the other, so I'll just write this as 1 over y equals, so I've divided by y, f dash of y over f of y ln of f of y. Right, now, can we integrate this? Well, let's hope to God you can. The left-hand side is going to be nice, that's going to be ln of y. Now, I would normally put absolute values, but we're told in the first part of the question, aren't we, that y is just greater than 0, I think. No, actually, no, I don't think we are. So I might put absolute value bars in. And that. Not that it really matters too much. Right. And now this right-hand side, so remember, we are integrating both of these with respect to dy. Okay. I'd be tempted to let f of y equal u and just see what happens. So du dy equals f dash of y. So dy equals du over f dash of y. Okay, so this is going to become, if we integrate this, this is going to be f dash of y over f of y ln of f of y. Actually, no, we're letting f of y, sorry. Our denominator is going to be, well, f of y is u, isn't it? So it's going to be u ln of u du over f dash of y. So that's going to cancel with that. So we have the integral of 1 over u ln of u du, which still isn't very nice. But I suppose we could still integrate that, and we're out of space as well, so that's not good. But let's say let's let v equal ln of u. Well, then dv on du is 1 over u. So du equals dv times by u. So this integral becomes the integral of 1 over uv times dvu. So the u's cancel. So it's just going to be the integral of 1 over v, which is ln of v. Well, v was ln of u, so it's actually going to be ln of u. And u was f of y, I think. What did we call it? U was f of y. So this is going to be ln of f of y. So ln of f of y plus some constant, because we always need to have some constant when we integrate and we haven't got any limits. Okay, so guess what we could do next is make this ln of y plus c over here. No, you might be arguing why is it not minus c? Remember, c could be positive or negative, it doesn't really matter. So ln of f of y. Well, you could also think, sorry, that you could we could have just added the c to this part of the integral. You don't always add the constant to the integral on the right. It doesn't matter. Okay, as long as one of them gets it. Raise this to the power of e, because we're interested in what f of y is. So raise all this to the power of e. So this is going to be e to the ln of y plus c equals ln of f of y. Well, e to the ln of y plus c, well that's e to the power of c. Well, e to the power of c is just some constant. Okay, so we can write this as k times by e to the ln of y, which is just going to be y. That equals ln of f of y. And now raise it all to the power of e again. We get e to the k y equals f of y. And well, e to the k times y, that's e to the k all to the power of y, right? Or raised to the power of y, because then they multiply. But e to the k, e is a constant, k was a constant, so this can just be written as another constant, like b. Okay, so b to the y equals f of y. I think that's it. Let's have a look. I need to find a better way of making these videos. If any of you have any ideas, please do let me know. Then f of x equals b of x. Well, that's actually quite a quick fix, because what we've got is we've got that f of y equals b of y. So if we just let y equal x, then what we end up with, that means that f of x equals b to the power of x. Okay, and there we are.